In the high-stakes world of AI development, there's this really mysterious, really expensive problem that keeps derailing massive projects. You have these AI models that are supposed to be getting smarter, and then all of a sudden, they just break. Today, we're going to dig into why that's happening and how the answer might just be a forgotten fix that's been hiding in plain sight this whole time. So what if I told you that the solution to this multi-million-dollar glitch wasn't some brand new, super complex algorithm? What if it was actually a piece of older, maybe even forgotten technology? That's the big question we're going to try and answer. Okay, so every good mystery needs a crime scene. And to really get what's going wrong here, we have to start by looking at a process that's right at the heart of how we make these AI models so incredibly intelligent. That process is called reinforcement learning fine-tuning, or RL fine-tuning. The best way to think about it is like special forces training for an AI that's already pretty smart. It's how we teach them these really advanced reasoning skills. But here's the catch. This whole process is unbelievably fragile. It's super sensitive, and it can go wrong in a really, really spectacular way. And this right here, this is our crime scene. It's called training collapse. Picture this. 1 minute, your AI model is learning. It's getting better, things are looking great. And the next minute, its performance just completely nosedives. The whole training run is a bust. We're talking about a crazy amount of wasted resources, time, money, thousands of hours of computer power, just poof, gone. Now, for a long time, the AI community had a prime suspect for this crime. They called it the Training-Inference Mismatch. See, to be efficient, these AI systems use two different engines. There's a training engine, and then there's a much faster inference engine for when the model is actually being used. The leading theory was that tiny differences in the math between these two engines were adding up over millions of steps, basically snowballing into a huge problem that caused the whole system to crash. So, with the mismatch pinned as the prime suspect, the race was on to find a fix. But you know how these things go. The first attempts went down a really complicated and, as it turns out, totally wrong path. What researchers came up with was this whole suite of really complex algorithmic patches. You can think of them as these intricate mathematical band-aids. They were designed to constantly try and correct for that tiny mismatch while the training was happening. But these band-aids, they honestly created more problems than they solved. For one, they added a ton of complexity, and they tacked on about a 25% extra cost to a process that's already incredibly expensive. On top of that, the models learned way more slowly. And even then, the patches weren't actually fixing the root cause. They were just covering it out, which meant you still had a performance gap when it was time to actually deploy the model. So the investigation was pretty much hitting a brick wall. All these complicated fixes just weren't cutting it. It was clearly time to look for a different kind of clue. One that was hidden on a much more fundamental level. And this is where the story takes a really fascinating turn. The researchers started asking a very simple but profound question. What if we've been chasing the wrong suspect this whole time? What if the problem isn't some high-level, fancy algorithm, but the very format of the numbers being crunched by the hardware itself? Okay, so let's meet our two main players here. On one side, we have FP16. It's the modern standard. Its superpower is a massive range. It can represent unbelievably big and unbelievably tiny numbers. But its hidden flaw? Low precision. On the other side, we have FP16, an older format. Its superpower is super high precision, but its range is way more limited. It's kind of like this. BF16 is a 30-foot ruler that's only marked in feet, while FP16 is a 1-foot ruler marked down to the millimeter. And here's the technical trade-off, put simply. Both of these formats use 16 bits of data, right? But they spend that bit budget differently. BF16 spends more of its bits on its exponent, which is what gives it that huge range. That leaves fewer bits for the mantissa, which controls its precision or level of detail. FP16 does the exact opposite. It prioritizes precision over range. And this one little design choice, it turns out, it's everything. Because this tiny difference in how they spend their bits, well, that's the key that unlocks this entire mystery, and it leads us to a solution that is almost laughably simple. So here it is, the real culprit, the whole time, was BF16's low precision. Its lack of detail meant that tiny, seemingly insignificant rounding errors were happening with every single calculation. Now, over the millions and millions of steps in AI training, these little errors were adding up like a snowball rolling downhill, getting bigger and bigger, until the training and inference engines had drifted so far apart that the whole system just collapsed.
And the evidence, it's just crystal clear. When the researchers ran their experiments using the standard BF16 format, the training runs were unstable. They collapsed all the time. But when they simply switched over to the high-precision FP16, the training was stable. Just like that, the problem was gone.
But wait, because it actually gets even better. Using FP16 wasn't just more stable, it was flat-out superior. The models learned faster, and they ended up with higher performance scores on all the benchmarks. So this wasn't just a fix, it was a complete upgrade across the board. You don't have to take my word for it. This quote right from the research paper says it all. The solution wasn't some new algorithm, it wasn't a complicated patch, it was, and I quote, simply reverting to FP16, which effectively eliminates this mismatch. And really the most beautiful part of this whole story is how simple it is. The fix doesn't require any new algorithms, no fundamental rewrites, it's just a configuration change. We're literally talking about a few lines of code to tell the system, hey, use FP16 instead of BF16. A simple switch that solves a massive, industry-wide problem. So that leaves us with one final nagging question. If FP16 is so amazing for this, why did the entire industry abandon it for BF16 in the first place? How did this old tech win? Well, BF16 became the standard for a very, very good reason. When you are pre-training one of these giant models from scratch, that huge dynamic range it has is an absolute lifesaver. It keeps numbers from getting way too big or way too small, a problem called overflow and underflow, and that made the whole training process much more stable. For that specific problem, it was a brilliant solution. But, and this is the key to everything, for the very specific job of RL fine-tuning, that extreme range just isn't what you need. The model's numbers are already kind of locked in. For this particular task, the high precision that BF16 gave up is actually the most critical factor for success. It's a classic case of using the wrong tool for the job. So what can we all learn from this whole detective story? Well, first, that the default option isn't always the right one. Second, that sometimes our most fundamental choices, like numerical precision, can matter way more than layers of complex algorithms piled on top. It just goes to show you that real innovation can come from going back and questioning the basics. And finally, it's a huge reminder that you always have to pick the right tool for the specific job you're trying to do. And that leaves us with a final thought to chew on. This entire expensive industry-spending mystery was solved by looking backward at an older piece of technology. It really makes you wonder, doesn't it? What other complex, modern problems are we trying to solve with complicated patches when a simple, forgotten solution is just sitting there waiting to be rediscovered?